Okay, welcome all of you. Today we will learn more about threads. I gave an introduction on last Wednesday. So we'll spend some more time on using some of the methods that are available in threading and how can we create multiple threads within a process. Okay. So what I plan to do is I will make small files so that it doesn't run for long, and then you also may be able to understand it better. So we will have multiple files coming out. Now, last week we stopped with a question on who can join or wait for a particular thread to exit. We will see that before I continue further here. Okay, let me just refresh. It's 1 week. I don't know whether you remember what we were discussing. We have a class, myThread, inherited from the built-in threading module, and in that threading module there is a thread class which we are inheriting. This is a generic thread creation class. Now when we inherit, we want to override the function run, but we are not touching the start function, which is also a module of a method of thread. Now in it we have some properties, object attributes of a thread. Now since we are inheriting from the module thread, this itself is a thread object, and we have our own attributes within the thread object. And what is this method? As I mentioned, when we create a thread, it doesn't run automatically. We have to say start. When we say start, which is not given here in the method, that means it is there within that which we are not overridden. So it will be calling, if it is not found here, it will call that function method, and then it will start the thread. And when you start a thread, it automatically calls run. So when it tries to call the function run, since we have overridden it, it will be calling this method. So when you start a thread of this object, automatically this gets called, run gets called through start. Okay, and we can also call run directly. I will tell you the difference between the starting a thread with a start and then making a thread to run using this function, this method. Now what all we have? We have some name, delay, initial count, and then we are stepping down with some steps. So we have a function within our, which is getting called by the thread, and that is called thread countdown. If you see, this is not part of the class thread. It is part of this process, which is this Python program, which is called by this interpreter, which is a CPython running here. So this method itself is not defined within the thread. It is within the process which is calling this thread object or initiating the thread object. So the fact that we are able to call this method from inside a thread means that each of the threads which is running in the process have access to all the variables, methods, and the attributes of a process, which is this main thread. Okay, we call it as a main thread now. Now what is this method doing? It is just taking these values. I think then it is printing the thread name, which is calling this method, because this method is common for all the threads. So we may create multiple threads and each of them are going to call this function. So we want to know which thread is calling this function. So I am passing the name to this, and then it is going to decrement some value and print it. Now when they are printing, all the threads are printing it on our standard output. which is coming on our screen. But you may see that this output coming from these threads may overlap. The reason being they are all running in parallel on multiple cores maybe. Then you may see that this outputs may get gobbled out when it comes out, okay, on the console. Okay, now you understand that we have made a thread class inheriting from the thread of inbuilt class, which is from this threading module. And because I'm stressing on it, because in the later part of the day, we'll learn about thread pools, which is a little different from the threading that we are talking about. So here we are using the threading module, which is creating threads. Now what do? We create a thread object. So main thread, I am calling this as a main. Whatever I am printing it here, I am calling it as a main, because this is the main process or thread which is creating multiple threads. But whenever I am running here, this run could be for different threads by different threads. So I am printing that value, which is nothing but the name of the thread which we pass it while creating it. So we will know which thread is actually printing this output. So I'm saying starting a thread and then finishing the thread, because once this function exits, okay, the run function exits, this thread is no longer running. Okay, there is nothing holding it back. So the thread is finished. So now, if you remember, if you are familiar with Unix or Linux environment, any process which is created by another process, which is parent, and this is child, always every process has a parent. I am talking about Linux. Every child has a parent. Now, when the Linux boots, you know that init process starts. That's the first process which is created by itself, not by any other parent. Then any other process that is getting created in Linux environment is by a parent. Either init process itself will be creating other processes, or these processes may call some other process. So every process gets created by a parent. Now there is a little difference is there in when I say this, because there are user level processes and kernel level processes. There are kernel threads in Linux. They don't get created here, but they can be created by other thread create routine internally. And this is the user level, user mode, and this is kernel mode. So these kernel threads run only in the kernel mode in Linux, whereas the user threads run in the user mode. But does it always run in user mode? It's not the case. When they call some system calls like open file or write into a file, they need to get the operating system's services. So they call system call. Then what happens is the mode changes, because if you have to run a system call, which is part of the kernel, they need to be in the kernel mode. But initiation is from the user process. Maybe user 1 process and user 2 process also may call open file. So what happens during that time is this open file is a kernel function which runs in the context of a process. So what I mean by that is they have kernel stack, separate kernel stack. See, always the processes which are running in the user mode and the kernel mode, which is differentiated by the particular bit in a processor CPU, which will decide whether the processor is in which mode, whether it is in user mode or kernel mode. Once it is in kernel mode, you can only execute kernel code. You cannot write your own code. You cannot make the user program to run in the kernel mode. Unless you write a device driver and make it part of the kernel, it's not becoming a part of the kernel. Your user code will remain as a user mode only. You cannot make it run in the kernel mode. Now, when this runs on the kernel mode, what happens is you cannot use the same stack that user processes are using it, because which is not very reliable. User processes stack memory is also everything is in the main memory. Kernel is also in the main memory. User processes also in main memory, but they do not have a condition or restriction that even though other processes cannot access it, they are not safe enough because user processes may misbehave and you cannot use the stack. So what happens is during the kernel mode, kernel uses its own stack, kernel stack, but it runs as a part of the process. So they run in the context of the user process, but they have their own stack and they execute the kernel code. Now, when we talk about, why did I talk about all this? Because the parent-child relationship always is there. Okay, any process. So when a process dies, a child process get killed, they they get into a zombie mode. Okay, a state, not a mode, state, zombie state, which means that they are no longer you will be able to run. It's already finished its job or maybe killed in the middle, but they cannot be they cannot be made to run, but they are not killed completely, they are not removed completely from the memory, they are in a zombie state. It is kept in this state because parent process is running and it might be interested in saying join, I want to know what has happened to my children. In that case, there should be a state of this child available to the parent so that it can get the information about what happened to the child, what how it got killed, whether it is a normal termination or somebody sent a control C signal, or some root level user has killed it. So there could be some many reasons for a child process or any process to get killed, and that parent may be interested to know. So always there is a relationship with parent, and the parent can decide to say I want to join. That means I want to wait for a particular child. It can say that I want to wait for a child. Then it will be called with respect to a child object, thread object, or it can also, apart from that, it can also say time. I want to wait for such a long time. If suppose parent is waiting, but child is still running, it has not been terminated, parent can decide to do something, but if it is waiting indefinitely, then it will, there may be, it has to wait. But you can also say that I want to wait for a particular time. If the child doesn't terminate and it doesn't get notified to the parent, then it will come out of this function saying that child is still running, it's not terminated yet. What if child has already exited? Then it is in the zombie state, which will come immediately notify the parent that child is terminated for such and such reason. Then it can continue further. So this join function, what we see even here, is actually to say that it is waiting for a child object, child thread to terminate. This is the child one, and then this is a timeout. I'm not showing whatever is a timeout, but we have a function here which we can say timeout. Otherwise, it is assumed to be indefinite and it will wait for a particular child. So Unix or Linux also has the same join function, which a parent can wait for a particular child or it can wait for any children to terminate, and then it can be woken up. So when it happens, when a parent executes the join, it is stopped. It is suspended. This process is suspended, waiting for the event to happen, which is nothing but the child process getting terminated or getting killed, and then the parent process getting notified. So this is what is happening in a Linux system, as well as when we are running it here, when we use join, we do the similar thing here. Now, what we do, we say my thread, create a thread object. We are not yet started running it, or we are not made it even start it. So we create two objects, thread A and thread B, and then say start. Then this function was not overridden, so it calls the start function method in the thread, and then which in turn calls the run, which gets resolved here, and this getting called. So at this moment we run this. That means the thread has started running. Now this main thread which has started the thread A waits for some 0.1 second and then starts B, then says I want to wait for thread A. And when there are no parameters here, it means it wants to wait indefinitely till thread A exits. Now when will thread A exit? Thread A will exit when it, based on the count, we are saying 0.5 second. I think there's a delay, and 5 and 1. Increment is 1 and 5. That means 5 second, 5 into 0.5 second, because 0.5 is a delay which is inbuilt into this. This thread A calls this function, which is into a while loop till the counter, which is starting with the 5, decrementing by 1, and in between there is a delay of 0.5 seconds, so it will keep on going. Now during this method, when it's getting executed by thread A, this same method is also getting executed by thread B also, because thread B also gets the same object, same run, and it is going to call the same method. So this method is a reentrant method. Okay, this is a reentrant method getting called by both thread A and thread B, and but with different parameters. So this clearly says that we have these local variables, which are parameters, as well as the local variables. They are all in the stack, and they are all in which stack? They are all in the thread stack. So let me explain about the stack philosophy. When a parent, this is our main thread, is calling thread A, getting created, thread B is getting created. Now when these threads get created, they have their own local thread stack. Okay, so all the local variables of this main function, whatever the thread count function is, the variables are here in this copy, and this has its own stack, and all the variables that we are passing, they are all here. So their state is individually maintained, so they are not overlapping with each other, whereas the method as such, whatever the method or the code of this function is common. It is executing from the same memory. So both thread A and thread B are executing the same code, but they maintain different stacks, so they have a different state while executing it. And they also sleep for a long, different time, because internally we are calling the sleep, which is with a different parameter, because that is coming with a 0.5 here, whereas here this also 0.5. I have passed the same value, but it could be different also. So they understand this clearly, that this method is a common single code which is getting executed by two different threads with multiple parameters, various different parameters, and they are all maintained in the stack of those threads, individuals, and they have their own state. So they run multiple times, 5 times or whatever iterations, and the step is here 2 and step is here 1, but effectively they run 5 times. Now during that time when they run, the main thread is sleeping, in the sense it's not sleeping, it is waiting. In the sense it is suspended, waiting for the event to happen. When will that event happen? When the thread A exits. When it finishes, say, finish thread A, then who sends the information? The background operating system, as well as the thread main object library. They take care of informing this and waking up this particular, this waiting on this thread A. And then we are waiting for thread B. The main thread is now waiting for thread B, because we started the thread B little later than thread A, though they have the same iteration, same delay. Thread B will finish it little later, and I put it in this order. Otherwise, what will happen? Suppose if I put B and A, still it will work, because as I mentioned, as a Linux, all the processes which are dying early, they will be maintained in the zombie state, and the parent will be informed. So even if you put it B and A, we can try it out. It will work. It will come out immediately. Only thing is, it will come out immediately, but both thread A and B. Okay, then it will say that both threads have come out. So this is what we saw last week. And let us try to understand the running of this thread. So we create the thread A, thread B, starting the thread A, and then this is saying, this is by, I'm going to start the thread. So we created the object, but we are not started running it. Once we say this and we start the thread A, you see here, going to sleep is coming later, whereas starting thread A is coming first. So what does it mean? When I say start, there are, it's like a Unix fork is there. One is forking to the child, another one is coming down to the parent process. Now, if it prints this, it is printing from the main thread. If this is getting printed, it is getting printed by the thread which is created newly and which is has its own life and it runs parallelly. Now, why is it coming first? So what happens is normally, okay, even in Linux, when you do fork, there is a copy on write or delayed write where the same image is created, and then when you execute, a new thread is getting created there. So they actually, let me, maybe those who know Linux will understand it, or if it's okay. When you do fork in Linux, what happens is it returns twice. It comes back to the calling function twice. It comes back from the fork twice. One with the PID of the child, okay. Another one is with the PID of 0, which means that it is a parent copy, and this is a child process. Now within fork, what you do is normally when you return equal to not equal to 0, we say that it is a child process, and then we call exec call, which is nothing but putting a new program here, okay, new process here. Otherwise, what will happen is, it is both the parent and child are running the same image is run, though there are two different lives, there are two different threads, PIDs are created, process IDs are created, but they run the same code, and it is called COW, copy on write. When any one of the, either parent or a child, makes any changes to the parent thread, then a new copy is made, a child copy is made. But prior to that, exec call is you do, then you overwrite, you don't even create a copy, but you create a new program with a exec, where the child process will be executing a new program. It could be something new. So to do that, in Linux, actually, when you do fork, you have two processes now. Parent process is there to run, and then child process is there to run. So the scheduler decides to run the child first, then the parent, because the child is likely to execute this function call, so that the copy on write will be saved. Okay, normally what happens is, when you create a child process runs first after the parent process is running. Okay, that's how the scheduler decides the order in which they are run. So you see the similar behavior here. Okay, I'm just comparing the Linux because I noticed the similar behavior. Okay, when you do a starting thread, okay, we did starting the thread A. When we did that, when you do start, the execution goes there, in the sense it gets it is getting executed, and you are getting the printout first, and then you are getting the print of this. Okay, that means this is getting printed later. Okay, so it gets printed, and then before it goes to thread count and then does something, you get a printout from the going to sleep. Okay, this gets printed, and then it goes to sleep. Then what happens during that 0.1 second, thread A is running, okay, and it is printing 5, and then by the time it woken up and it starts the thread B, okay, then you see here main start thread B, starting thread B is there. Now thread B is also executed first. When you start the thread B, again the child is getting executed first, and then it says that I'm going to wait for both the first thread A to finish, then the main thread is going to be suspended, and these two are running in parallel, but they sleep in between. So that's why you see that the prints are coming after some delay. Both get terminated. No, they come down to 0. Then one after the other, they get finished. Now thread A gets finished, and then thread B gets finished, because we are saying we are waiting for join thread A first and join thread B first. Okay, here next. Now suppose if I do, just for the sake of, I'll come back. I will change it back to original. I want to just show you that even if you do this way, it should work. And the zombie, whatever I explained, should be here. So let us check. Okay, thread B, I'm starting. I'm sorry. Yeah, thread B, I'm saying join, and then thread A join. Okay. Now what happen? What happens? Same thing is going. Now you see here, you can see that suddenly this gets fast. Okay. Let me just, you notice that it came out very fast. Now let me just go back to the old one. If you are very keen with your keen eyes, you can see that they don't come fast quickly, but okay, they both, because I have given the same count, it is doing it. Maybe if I change the count little bit later, this thread B, let me finish it later. I am giving more time for it to finish. So let us see. Now we are waiting for A. Thread B is going to run for a while. Okay. Oh, I did something. It went into a negative loop. Okay, I should be very careful. Oh yeah, 2 is there, so it whenever comes, I should put a even number. Now how do I kill it? Okay, how do I kill it? This thread is going to run, thread B is going to run till it comes back and see some negative decimal, okay, even number. So only way to kill it is, I'll tell you. Now this thread B is still running. It is running in the context of this particular interpreter, Python interpreter. Okay, so if I have to kill now, I can do one thing. I can do a control C here. It doesn't accept it. Okay, I gave control C but doesn't accept it. Now only way to kill it is to kill the parent. Now what happens in the Python is implemented in such a way that when you are killing the interpreter process itself, which has created multiple threads, they do a cleanup and all the threads will be killed when this particular interpreter is dying. So how do I kill the interpreter? I close it, force it, and then what happens is that thread gets killed. Okay. Now the problem was I put a even number instead of even number, I put a odd number. So hopefully I think this should solve the problem. Let us see. Okay. Now you see here, I put a thread A finish. First I was waiting for A and then still B was running. So it waited for B and then it completed. Now if I change it, the order of join, I want to join for B first and then the A. Now what happens? Actually, you know that thread A is going to be finished early, but the parent is not waiting for thread A to join. So it is waiting for, please remember when I say join means it is waiting for thread B to terminate. So it is waiting for thread B to terminate. By the time thread A also would have been terminated. So if I do this, what happens? Let us try now. What do you expect to happen? Both are finished. You can see that now this is finished thread A, main thread A finished. Okay, actually misnomer, I should have put B. This get printed and then going to wait, then thread A is finished. Okay, so this is what is the message. Whereas this is coming from, finished thread is coming from the run function. So it has finished much earlier than B, but main is coming out after the B is done and then A is done. So that means what? Even though parent was not waiting for thread A join, it comes out without any issue, even if a thread A has already been killed, so or finished. So that's what I was saying. Linux also maintains a zombie. Here also that information is maintained in the Python, that even if the parent doesn't call join, it maintains the information that it has finished. So after B came out, it immediately comes out saying that A is also done. Okay, that's what I wanted to make it clear to you. Maybe I may ask you to explain what is happening underneath, how main thread comes to know about this thread getting finished. Okay, so I hope this is clear. Now the question, any questions from any one of you? Okay, I'm just going on my own. Okay, fine. Now there was a question yesterday or last week that can a thread wait, not a main thread, can another thread wait for somebody else, its sibling, okay, we call it as a sibling, to terminate. Now we have to change a small make a small modification to this code to make it happen. So I have written a code as I told you last time. So let me take this. I think this will only explain a particular thing. Okay. 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 Now what did I do? I am using the same code like what we have understood now, except that I am doing some small change in the run program. Okay, I have made some changes in the run program. So let me explain you. We are creating a new thread A and B using the run program. So this run program is going to be executed by the same code is going to be executed by both the thread A and B. But we want a different control so that we can say that one particular thread, if suppose if it is a thread B, name is B, I want thread B to wait for thread A to be done. Okay, let me explain what I am trying to say. We have a main thread here, main thread. It is creating thread A and thread B, and then I want this thread to wait or join on thread A. Okay, to join, that means it is thread B is going to wait for thread A, its sibling. Now, how do I implement it? Okay, how do I implement it? Same run function. Okay, I am printing that I am introducing some new function which is threading dot current thread dot get name. So this run may be called by two instances, thread A and thread B. I want to know when I am executing it, which instance of thread is running. So there is a built-in function which is current threads get name. So current thread means whichever is running, whichever thread instance is running this code, its name is printed. Now what I do, I use the built-in method get name, which is effectively giving the name of the thread which is executing this code. And then it may be using the self.name because internally name is the variable used to know the name of the thread. Okay, now or it is maintained internally by the library. Okay, because we are passing a name which will be used by this particular method to get the name for us. Now imagine I'm going to create a similar way. I'm going to create both thread A and thread B with the names of A and B. So I am checking whether the name happens to be B. Why am I doing that? Because if I am going to wait for thread A to join, it should be other than thread A, it should be other processes can do, but A cannot do. Okay, I can put a not of A. Yeah, thread A, because the same code is going to be executing the thread A is also going to execute the same piece of code. If it executes thread A join, it's going to be a deadlock because it is waiting for itself to be terminated. So how can it wait for its own termination? Because until it comes out of the join, it cannot be called terminated. It has to complete the run function to say that it is completed, but it is waiting for itself. So it's a deadlock. Okay, you cannot call this thread A join cannot be called by thread A instance. So to make sure that it is not a I am checking whether the name of the thread is B. Then I say I want to wait for thread A to join. thread A join. That means what? Thread B is going to wait till thread A completes its job, and then only thread B is going to run further. So in this case, what will happen when you see the output? Thread A is going to print all of them, all their countdowns after the delay. It is going to count down to 0. When thread A ends, then whoever is waiting for thread A to get terminated will be woken up. So how is it implemented internally? Now you may wonder that how does the operating system know which thread, who is waiting on this particular join? Okay, so there is a queue maintained by internally by the operating system. Okay, any thread can say that I want to wait for particular guy to finish. Then when the thread A gets killed, it will notify all the threads which are waiting on this. Okay, now we see that you can even say that thread A, this join can be executed by anybody, and multiple processes can do it. See, don't think that it can be only by one person. It can be one code. It can be multiple instances can execute this, and all of them will be woken up when this event happens. So that's how OS manages it. So there is a queue maintained. Whoever is calling thread A join will be put in the queue till the thread A executes its job and then exits the execution. Then if anybody is waiting, it will be notified. Now if nobody is waiting but it is in the zombie state, then if somebody comes later on to say that I am waiting for this, they will be woken up immediately. They will not even put in the queue because it is already died and the zombie state is there, so they will be woken up. So this is how operating system manages that, and we have the similar thing here. So now you may have a doubt that how come thread A is available here, because that thread A is a object in this process. Okay, this main thread process. So thread A and thread B, they have a different instances, but still they have access to this object because I told you all the threads share the process namespace. So this is the main thread process space is shared by all the threads. So thread A is accessible to it and it can wait for it. Okay, so now what happens? Only thread B will wait here, whereas thread A will see that it is not falling into this category. It will run as it is. So thread A will run first, even though you are creating it one after the other. Thread A will finish first. Till then, thread B will be waiting for thread A to exit, and then thread B will do its job and come out. So finally, when this waiting is happening by the main thread, it will see, I told you that this join can be executed by many places by many processes. So one is executing here, which is done by thread B instance, and the other one is a main thread which is also executing the same thread A join. So both will be woken up when thread A exit. Okay, it depends on who does first. Okay, in this case both would have done waiting on this. If you look at the timeline, maybe I will explain you based on the code. I will explain you the timeline. We are creating thread A. Main thread is first created. Okay, when you run the program, main thread is created. It runs. This is the Python program. Thread A is created. Thread B is created. Now thread A runs loops 5 times loops with a delay of some 0.5 second. Now thread B is created. It comes and say thread A join. So it is stopped. It is stopped. It is going to wait for thread A to finish 0.5 second into 5 times. Now what happens with the main thread? It continues here. It sleeps for some 0.1 second and then it says that thread A join. So this guy also, the main thread also wants to wait for thread A to the end. So this is also stopped. Now on the screen what you will see is output coming from thread A only. You will see output from thread A only you will see, and then 5 output comes, then both will be woken up. Both thread B also will be woken up and main thread also will be woken up, and then based on the scheduler and based on the availability of processor, whoever gets a chance to run, they will run, and then they execute the remaining portion. Now thread B, what it will do, it will continue after this 5 times iteration. By the time this guy is going to execute thread B join, so it will be going to wait, it is going to wait, and then when this guy finishes, then main will finish and then everything will be completed. So that is what will happen when you run this code in this case. Now let me run it. So this rest of the code I have explained you. This is what is written. Now see here, thread A only is running, and then thread A is finished. Thread B is woken up, and main is also woken up because it was also waiting for thread A to finish. Now main is going to wait for thread B, so it is stopping. Then thread B only is running. Then when thread B finishes, main is woken up and both threads are finished. So this is the sequence I explained you is happening. So it is possible that anybody can wait on this because we have the object and any thread is able to wait on the event for the thread A to end or terminate. Okay. I hope this is clear. I will give some time. Yeah, go ahead.
Sir, how the thread A variable is available in that method?
Okay.
Number 37.
Okay. See, okay, let me explain with the picture. I told you that this is the main thread, though I am calling it as a main thread, is a main process. Okay, this is a process, and it has a data memory. Okay, data memory. Within the data memory, there is a thread A object, thread B object, variables. These are all variables. The object itself will be lying in the object memory, but thread A and thread B are all there in this object, in this data namespace. Okay, this namespace. Namespace, when I say, it's a area, memory area, data memory area, which is visible, accessible to both thread A and B, which is running in the within the process, because the fact that thread creation of these two is done by the main thread, it is running in the context of this main thread. So any variable in this data memory, which is nothing but these variables, are visible, accessible to both the threads. Now, what is this run program? Run program is a code which I told you that is a common code which is getting executed by multiple instances. Both A and B are executing it. And when it is executing it, you get a different object here. Okay, the self.name is for the thread B instance. This will be true only when thread B instance is executing it. Whereas when thread A instance is executing this code, this will not be true. So assume that thread B instance is executing it, it will be true, it comes in, and when it looks for thread A in Python, this is like a global variable. Okay, it's like a global dictionary. So it will look into the global dictionary which is visible or accessible to this thread. So that global dictionary will have the thread A label and its address or location where it is. So this object is available. So it can then, once this thread A object is available, then it can execute the join method on it. So when it executes the join method, now what happens is the thread module, the threading module for that matter, takes care of stopping this thread, putting it in a queue, waiting for the thread A to finish. So that's where this instance goes into sleep. So if you see thread B comes here, thread B, if you follow the thread B starting, thread B is starting, which is getting printed. Okay, this is starting thread B. Wait a minute, sorry, I will come again. When you created it, then thread B, starting the thread B, main is saying, then the current thread's name is B. Who is printing it? This thread B's instance is printing it. That means thread B has come here, it is executing it, its name is B, which is getting printed. Now it says thread B, starting thread B. Okay. Actually, this way shouldn't have been starting, running maybe. Okay, so this is getting printed. Okay, this is the instance of thread B. Now, where is this coming from? Okay, this is coming from this. When it goes into this, it says that thread B going to wait for thread A to complete. So now this is getting printed, and then you see that there is nothing of thread B after this. Why? This guy is now in a blocked state. This thread is stopped there, waiting for thread A to do it done. So that's why you see that after this, what you see is main going to wait. Now main is coming because both are given the CPU one after the other, and both of them are using the same output port, COM port, this SDDI output console. So it is printing the mains going to wait for thread A finish is coming. Where is it coming from? This one. So it slept for 0.1 second after starting the B. So during the sleeping, so many things happened with the thread B, and then during this time thread A is sleeping after printing some output. Okay, did it print anything? Thread A, no, thread A did not print. It is printing here. So it is in the state. Thread A is maybe not able to get a CPU, so it's not running. So now thread B, main thread is running, and it is also stopped. Now main is also stopped. Now after this happened, both of them stopped and the rest of it is running. Okay, now I hope you understand that how it has an access to that because of this understanding that the threads are running in the context of a process, which is nothing but the main thread. Is it clear? I didn't hear you.
Yes, sir.
Okay, fine. Now I hope others also understood this sequence. Maybe in the exam I will ask you to, maybe in the end exam I will write some small code and then ask you to explain what is happening. Maybe you will cut and paste and run it, but even then you may not be able to do it very clearly because it is going to take time, and I may expect you to explain it in words, your own words. So it will better that understand these sequences, what is happening, and have a good understanding of this multi-threading business, because it's very important that not only for Python but in general it is good to have a knowledge on how multiple threads run and they are managed by OS. As a software engineers, it is good to know that. Okay, now I hope this is clear. Now how much time we have? Okay, I think almost we have finished the come to an end. So I will continue with the threading business at 8 p.m. Okay. Um, I will not. I will call them as the 14B only. Okay. I will call it as 14B. Today's class is 14B. So this is the old one. So we can stop here.